make some noise again. Woohoo! So, for years, it's been a dream for us to have some guys from Amazon that will share just a little bit of NDA. And today we have a chance. So give a big round of applause to Victor and Mike. I'm counting on you.
Thank you very much. So, first of all, hello everyone. My name is Victor. I am developer advocate from AWS. And together with my best friend, the best solution architect in my life, principal solution architect Mike, we are going to speak about some secrets from AWS. That is true. So, yeah, absolutely. So, the main idea today to show you exactly what's under the hood of Amazon Aurora. And you will not find this information in official documentation. Again, yeah, you're absolutely right. So, again, a little bit disclaimer. For sure, I will try not to open all of our secrets. And I see very mature speakers, very mature people here. And if you ask us a little bit deeper, which we cannot open and show you, because again, it's NDA, I'm sorry. So, Amazon Aurora. First of all, before I will switch to the next slide, first question to you, how many of you knows what is transactional database? Please raise your hand. At least I see a couple of hands. Okay. Have you ever been in a situation that you run your database on some virtual machine, for example, and around the evening on Friday, you figure out that some changes in your code, amount of the customer stay too much. And currently, the performance of your database is so slow that you have to scale somehow. And we remember sometimes for transactional databases, it can be very terrible to scale, especially if you're based in one host. That's happened with me. I know what's about you, and I imagine like, okay, maybe we have some solutions, just like I can scale Limitless. And as you can see in our topic, we are going to show how Amazon Aurora can scale Limitless. What's exactly Limitless? But before we jump into there, let me share a little bit of the story. For example, you want to deploy your first database. What you will choose? Most probably you run your virtual machine, deploy MySQL, or as I heard from the community, Postgres currently is default configuration. Just like if you want to run your some database, most probably you will select Postgres. Okay, in Amazon we have EC2, virtual machines, great. After that, if you provide database as a service inside in your company, evolution step will create some managed service. Exactly what we did in Amazon, RDS. If you're familiar with AWS, most probably you had EC2, RDS, Dynamo, and these words. Today we will speak about them like a lot of time. I will mention and compare a little bit. Then we decided to move on and release the first version of Aurora, supported only MySQL. The next one is Postgres. Then we added new functionality, serverless, and finally, the last one, just like during the last reInvent, it's our biggest conference, we released Amazon Aurora Limitless. I already say a lot about like what's the history. You already understood Amazon Aurora, it's transactional database, but what exactly Amazon Aurora is? First of all, I want to highlight it that Amazon Aurora, it's compatible for sure with MySQL, with Postgres, and it's cloud-native database. When I said cloud-native, it means like when we designed Amazon Aurora, we already had all of our infrastructure. I mean like design of regions. Regions, it's a place where we put our availability zones. One availability zones, it means one or many data centers. And for every region, we have at least 3 availability zones. So, and also based on our services from compute, from storage perspective, we design our database. So, in very short explanation, Amazon Aurora is distributed fault tolerance storage. We will speak about storage a little bit later. It can be scaled up to 100 plus terabytes of your data. If you have high load application, and I believe on our conference here in TIC, if you're also interested about high load, that you can scale up to 15 replicas in Aurora. That's great. But for sure, we'll not only take, like vanilla Postgres or vanilla MySQL and say, hey, currently it's a managed service and you can use it. We also implemented different type of the functionality, like a global database, backtrack, blue-green deployments. It's a great. But when I prepared this session, I did a lot of researches and figure out that Amazon Aurora is the fastest growing service in AWS history. And as I promised, today we are going to share a little bit of our NDAs, numbers. So you ask me, what is fastest growing? Can you say for me what's the numbers? Based on 2020, in 2020, we had 3,000 installations of databases inside in Aurora, and more than 100,000 of clients who use Amazon Aurora. And what our CEO, Andy Jesse, previous CEO, said, it's the fastest growing service in AWS history. Before that, it was Amazon DynamoDB. I believe you're familiar with that. So currently, Amazon Aurora is still takes this first place, fastest growing. But still, what's the architecture of Amazon Aurora? I didn't explain. I said a lot of great words about Amazon Aurora, for sure, because I'm from AWS. I cannot say we have a better databases. So in very simple explanations, what is cloud native and what's the main feature of Amazon Aurora that we have decoupled from storage and compute layer. So storage is a separate layer. And for example, if you want to write your data, we will store in 6 copies, which is spread between availability zones. Again, availability zones, this means one or multiple data centers, and we have 6 copies. In every chunk of your data, it's 10 gigabytes of data. And from the top, for sure, we have our backbone, it's our network, and the compute layer. The compute layer also, as you can see, it's spread between 3 availability zones, and it's fully undependable. So it means you can scale on different ways. For example, if you need more compute, you can scale on different ways. So for example, you can run in different availability zones, different type of virtual machines, of EC2 instances. For sure, we don't recommend to do it, but if you need it, if you understand, okay, I prefer to run, for example, in the middle of availability zones, one configuration with, I don't know, with 10 CPU, for example, in availability zone 3, I want to run with 16 CPU, up to you. But in my opinion, every time when we speak about databases, the secret sauce inside in the storage. Exactly what we are doing, what's the magic, how we store this data, how we can achieve this reliability, durability of Amazon Aurora.
Indeed, we are going to start with the storage because a lot of initial design decisions of Aurora are actually based on it. And as Victor promised, we are going to show you some of the internals. And the first internal thing is actually the name of this service. So we call it Grover. It's not something that is available to AWS customers, but Aurora and a couple of other databases inside AWS use this service. So first of all, Aurora's focus is around one component, and this is the log. In database, log contains pretty much all the things that are happening there. So we can review everything else as a manifestation of this log. And in Aurora, Grover contains the log. So how it works? First, the database instance writes redo logs to the storage layer. And for those of you who are more on Postgres side of things, like myself, this is exactly the wall stream. Then, the way that we work with it, we have chosen the quorum approach. And as Victor mentioned, we replicate the data 6 times across 3 availability zones. And for write quorum, we use 4 out of 6 nodes, and the read set is 3 out of 6. That's not the only option. So we try to plan for bad days. Of course, we hope that they never happen. But let's say there is a natural disaster. For example, tornado that completely destroys the several data centers in one availability zone, as Victor mentioned. So in this case, we cannot have the quorum of 6. So we can potentially downgrade to a quorum of 3 out of 4 for writes and quorum of 2 out of 4 for reads. Because, well, rebuilding data center will most likely take months. And then the database can scale back to the initial quorum. So then, how it works in the opposite direction. Database actually reads the pages from the storage. And you see the difference. It writes the log records, but reads the data pages. So what happens in the background is that storage layer Grover actually materializes data pages from the redo log records. So basically, it has a process which is similar to the one inside the database. But here you can ask, didn't you just mention that you have a read quorum of 3 out of 6? And data pages, they're quite large. So does it mean that you read each page 3 times? Well, the answer is, of course, no. So the same as some other parts of this presentation, I have simplified it a bit. In fact, what I called read quorum, we can better call something like repair quorum when we need to get the data to other nodes. What we have in database are LSNs, so basically the log sequence number. And each time when we do a write, we know which of the storage nodes contains all the records up to specific LSN. So the write node can actually quickly select one of the storage nodes and, sorry, not the write node, the database node can quickly select one of the storage nodes and read the data directly from there. We also store the latency for each storage nodes and we periodically update it, so we try to select the fastest in most of the cases. Sometimes we select not the fastest just to update our latency information. Of course, if for whatever reason the database engine crashes, when it restarts, it will lose this cache, so it will still have to do some quorum reads. But this is quite a rare situation. And finally, the backup process also occurs on the storage layer, so it backs up both the records as well as the data pages directly to S3. And the benefit of this approach is that the database engine itself doesn't get the performance impact. So now let's compare it to traditional database. And I will use Postgres as an example. In MySQL, of course, the details are quite different, but the approach is very similar. So let's start with the left side with traditional vanilla community Postgres. We have a page in our memory. And in this page, we have one tuple. Let's call it version 1. So now we introduce some changes into this tuple. And it goes to the wall stream, of course. But except for that, you can see that the full page also goes to the wall stream. And this is the correct behavior of Postgres. I will explain just in several seconds why it is required. Now, if we introduce another version of our tuple, make another change, it goes to val, but you see that the full page is not locked anymore, because Postgres only puts it to the wall stream first time we touch a specific page after it has been checkpointed. And in this case, there was no checkpoint. Well, at some point, we will still have to do it, so we have to durably persist the data on the disk, so we will do the checkpoint, we'll create the required data files, we will also, of course, archive the log files, for example, for disaster recovery and point-in-time recovery purposes. So it all looks great, but there is one caveat. In Postgres, the default page size is 8 kilobytes. Well, in the operating system, typically you have 4. So what happens when we try to write our data page to the disk and one of the writes fails? Well, this situation is called split block, and this is a hidden corruption. So what Postgres does is it exactly uses this full page image to actually put it over this corrupted block, and then everything works fine. So to be honest, I really like this approach. It's very reliable, but there is one issue. There is so much stuff in val that the recovery takes minutes. Now let's look at what we have done in Aurora. So we start with the same page in memory, the same tuple version 1, introduce the same update to it, and then it goes to val storage. And you can see the difference, that we don't put full page image into the val. And the reason for that is that we don't do checkpoints, therefore we don't do full page writes. So if we introduce yet another change, again, it goes directly to the storage. So now under the hood, as I've mentioned, we coalesce these log records into the data pages. And therefore, the recovery actually takes seconds because the database engine doesn't need to do this during the recovery. Now let's look specifically at this right side in more details, how exactly it works. So we will start with the top left corner, and we have some log records that are coming from our database. So as a first step, when we receive them in storage, we put them into in-memory queue. At this step, we also do the deduplication, because it can potentially happen that the write was successful, but then, let's say, connection dropped between the database and our storage nodes. So the database tries to send this record once again, so we discard it immediately. Then we harden the records to a persistent storage, which is hotlog in this case, and only after this step we acknowledge back that write was successful. Now there are still quite a lot of steps here. So then, remember I've mentioned previously that we have write quorum of 4 out of 6. So basically, it can happen that some write nodes don't contain all the information. So what we do asynchronously in the background is we use peer-to-peer gossip protocol to get the records for missing LSNs. Again, we try to get them from the closest node to us to get the most performance, but it's not mandatory. After that, the fifth step, which I've already mentioned, we call these records into a data page. And as soon as the data page is updated, we first of all back up the record into S3, the same by the way we do for the page itself, and we mark it for garbage collection. And then both the garbage collection and CRC validation happen asynchronously. So a couple of observations here. First, all the steps in this process are asynchronous. And the second is that only the first three steps are actually in the foreground critical path of the latency. So what this means is that most of these operations that are normally done by database engine and affect its performance happen on the storage layer. And it has helped us to develop multiple Aurora features. A couple of them Victor has shown on the first slide. But one that I would like to speak about today specifically is an almost instant crash recovery. So if we look at the traditional database on the left, when it starts after the crash, it takes the checkpoint state and then replaces all the transactions after the checkpoint and until it crashed. And typically in Postgres, and by the way, when I say typically, I mean the default configuration, which is not always the best, but we see that most of the companies are actually using it. So typically in Postgres, the time between checkpoints is 5 minutes. And there can be a lot of stuff happening within these 5 minutes. And the problem also gets worse because this process is single-threaded. So now, what we do in Aurora? First of all, as I've said, there is no need for replay because we don't do checkpoints or full page writes. So in fact, the storage, so to say, knows how it works with records. So how to take them, how to modify them, and update pages with the information from these records. And another important thing is that it is done in parallel. Here might be the question, how can you do the log replay in parallel? Because they go one by one. If you apply them in random order, they will just corrupt the data page. And here the answer comes from the architecture that Victor mentioned. So we break down the storage layer into 10 gigabyte blocks. So basically each of these blocks or each of these segments can have its log records be applied in parallel because each data page is just present in one segment. Of course, it's replicated 6 times, but it's in one segment. So that means that this process is parallel and again happens in the background, so it happens continuously. And when we need to do the restore, yeah, maybe there are a couple of log records that are still not applied, but again, we apply them in parallel because of these 10 gigabyte segments.
Okay, secret sauce we figure out. It's storage. It's how it works. Thank you very much, Mike. And we continue to main dish. If someone of you knows me, that I am really like kitchen. So for sure, our main dish will be compute layer. So where you remember, yeah, Aurora, it's like decoupled. We have a storage we discuss. What's about the computer level? So in compute layer, let's imagine super simple example. You start your first database. For example, it's like you have very huge host with 200 plus gigabyte of memory and decided to run your first database, like 8 gigabytes. So operation system knows I have all of this capacity, and just in case when I need more memory, I can request it, database can request it from operating system and get this memory in scale, for example, up to 16 gigabytes of memory. Okay, but we see it's a lot of waste of the resources, and in AWS we cannot do it. You know, we calculate every cent. You know, you got your AWS invoice. You know how we restrict about the money, how we restrict about what we are doing with our resources. So what about if we just shared one host for multiple databases? For example, in this case, 16 gigabytes of memory for one database and for another one, 32. Sounds good, yeah, but what about if, in some cases, if we shared one operating system, one ecosystem, if other database decided, or somehow our other customer decided to take the data and secret data from another customer. So we don't rely on this solution. So for sure, in AWS, first of all, I want to highlight it, and I know some people not I would say, happy with that, maybe, I would say not this way. So in AWS, we decided for us to make sure that we have secure environments, it put everything in hypervisor, to put everything in virtual machines. We are not rely on containers, because containers is just like a process which shares the same kernels, and it means like we can be in the same situation when some customer take of something, I don't know, like for example, a data and so on, from another customer. So hypervisor for us is very important. But in AWS, we use a Nitro. Maybe if you're familiar with AWS, you heard about the Nitro. Nitro, it's hardware, custom hardware part plus software, which we use just like to virtualize our virtual machines. So, and in these situations, what will be? So, for example, the same case. I have a database. I run in virtual machine currently. I use a Nitro. So, and my database said like, okay, I need more memory, for example. Can you please give me more memory? But in these situations, operation systems know that they have only 8 GB of memory. And if we need to provide it more, it means like we have to somehow reconfigure this virtual machine and run new one. So it means like for database, it will be just like kill these virtual machines and run the new one with new configurations. So for database, it sounds like terrible. Yeah, I believe you was in a situation when you need to scale your virtual machines and start your VMware, for example, and so on. And for sure, it will be downtime and affect our users. So we decided to go a little bit deeper. So for that reason, we reinvent a little bit of hypervisor. It's Caspian. It's internal product again, Grover for storage, Caspian for compute. Caspian has 3 main components. So the first one, it's a heat management system. So we control how many resources someone use. Another layer, it's in the between the Nitro, what we already know, because through the Nitro we can guarantee the resources what you requested from AWS, like for your EC2 instance. We guarantee that you will use these resources. And doesn't matter that other customer currently has had some high load and so on. So still under the hood is the Nitro, but Caspian Hypervision, what he's doing, like he said, you as operating system currently think that you have the whole capacity of the whole server. And for example, when you run new database inside in this virtual machine, operation systems are like, okay, I have the whole capacity of the instance, and we can split it in multiple virtual machines. And for example, when I need more capacity, we provide it, because heat management from Caspian control who and how consume currently of the resources, and provided these resources for operation system and for our database. But what about if I have a reach limit of my host? Like I don't have any more operating systems, memory. What will be in these situations? Caspian will say, please wait, I need some time, and it will run additional host and migrate some of database instance to another host and provide the capacity of the resources was requested from the first operations system, from the first our database. And how we did it, because like as Mike already mentioned, based on our secret sauce from the storage and use Caspian as oversubscriptions hypervisor, we can create this one operating system and everyone can see like, okay, I have so many capacity. So the main point from here, Caspian is, it's live system. It's control all time, all of our databases. And this diagram, it's live metrics from productions, not from the whole production of AWS for sure, it's like some small part of the productions, but the main idea to show that the Caspian control who, where consume different resources from Aurora, I mean like in Aurora for sure. And when we see like, okay, maybe probably on this host we will not have enough resources, maybe it's a good time now to move some of the databases to another instance, because most likely, just like in a few seconds, we will request another resources for another database, and we can provide it. So we can be in situations that we most probably will say all time yes for every request of the resources. This is how currently works on the production.
All right, so now we see how we can scale our databases within one server. But what happens if the requirements of our just one database extend beyond the limits of this single server? Well, I guess the answer is quite obvious to most of you here. Database sharding is a well-known technique, how we can scale the database further than one server can allow. So we horizontally partition the data and then distribute it across several independent databases, which are called shards. So in sharding, one of the first things that you need to think about is your database schema. So there are multiple considerations here, like for example, you need to think about your frequent queries, about your access patterns, for example, so that the data that is used in these queries is located on one shard, so that it has the same efficiency as like a separate physical database. So that's something that we always do. We always think about our data model, we always think about our database schema. So should we just go ahead and use shards right away? Is it that simple? Well, I guess you know, the answer is of course not. Sharding is complex. And there are multiple challenges here, and we have identified 3 of them. So the first challenge is how do we route the requests? Of course, one of the options is that we can provide specific maybe libraries or specific logic within our application to do it itself. But that's not something that we wanted to do in AWS because we provide a service to our customers, so they expect like a single endpoint where they can send the requests. So we had to create our custom routing. It's unclear how to do this. Then the second thing is that we need, of course, to scale our database. And if we speak about massive scaling, we will likely have tens or even hundreds of shards. And this is a huge operational complexity. Except for that, normally the application load is not uniform across your whole database. So what this means is that you ideally should scale each shard separately. Because if you do it together, well, you will be wasting a lot of compute resources and money. And finally, to make it even more complicated, the question comes up, how do you handle the transactions that are touching several shards? So how do you do distributed transactions? So I will now go through each of these 3 challenges one by one, and we'll explain what solutions we have came up with. So the first challenge. What do we do with our routing? So basically, we have decided to create our own routing layer, not use any out-of-the-box solution. And there are a couple of design ideas that we have came up with. So the first idea is that we wanted to make this routing layer as lightweight as possible. So we have constructed it so that it has a small portion of slowly changing data. So basically the information about the database schema and about shard mapping. And what this allowed us to do is to scale these routers both vertically, which we do first, and then if needed, we'll also scale horizontally. And horizontal scaling also allowed us to put these routers into different availability zones for high availability, of course. Finally, we have decided that each of these routers would be a separate Aurora database. So it's not a simple proxy, but here and here, those are both Aurora databases. So what it allowed us to do is that now the routers can actually orchestrate complex transactions across several shards. And of course, then aggregate the results back to the client. And it also works with distributed writes, so it handles the distributed commit across the shards. Now, the second challenge that I've mentioned was about how we operate the shards and how we scale them. So basically, traditionally, in order to do this, you would have to have quite a lot of operational challenges, operational complexity. So you need to monitor each of them individually, you need to then scale them. What did we do? Well, again, Caspian, that Victor has just told about. So with Caspian, each of these database, it's actually based on the technology Aurora serverless, which we didn't talk much in detail today, but this is something we released a couple of years ago. So basically, Caspian allows each database to scale itself, so without looking at any of the other shards. And it's all great, but what happens when we get to the maximum size? So in this case, let's say we have a node that has 256 gigs of RAM. So what do we do after that? Well, that's quite similar to the situation that Victor has shown. So we clone our database, and then transparently under the hood, we update the request routing layer. And hopefully now it is clear why I was speaking about instant crash recovery. This is exactly something that we need to scale the database. So this new replica can come up within seconds. And the nice thing about this is that we actually have changed, for example, in Postgres, the buffer cache. So the buffer cache in Aurora no longer sits inside the database engine, and in fact, it's a separate process which we can also replicate. So what this means is that when the new shard comes up, it also doesn't have performance degradation because of empty cache.
Okay, we can scale, we figure out about the routing layer and so on, but still one of the main problem and where we need some secret weapon, I would call it, it's working with consistency in database. It's very important, yeah, especially if you work with transaction database. So how we can do consistency? So we have to have some sequence number, for example, for our Postgres or MySQL or something like that. So exist three main possibility solutions. The first one, you have a single timekeeper or who generated for you a sequence number, and you can guarantee this is this one, operations come later or after or before these operations. But if you look at these solutions, we have only one server who is responsible to provide this sequence number. So it sounds like not very scalable solutions. What else we have? Logical clock. Logical clock is a very interesting solution because, first of all, you can find these realizations, for example, in MongoDB or CouchDB, for example. What exactly is? So when some both nodes interact with each other, we increase the number. But if you look under the hood how it works, it's absolutely in a separate way how it works in Postgres and MySQL realizations. And this means like to implement logical clock for Postgres, for example, it will be over-engineering task. We did, for DynamoDB, for example, it's called vector clock. Yes, it works great, but for transaction database, for Postgres, it sounds like a little bit overcomplicated. And we are super lucky that we have the third option. It's clock, it's time. But you know, if you never look in detail what is time is, I mean like how to synchronize your multiple servers and make sure that you have the same time on different instances, you know, it can be a really challengeable task. Before we jump into some protocols and so on, if we run a couple of virtual machines and spread between, I don't know, or for example, just like put in one rack, in 1 month, we will see the difference in 1 second. Some of them it will be faster, some of them will be like less has difference between original time. But in 1 month we will see 1 second. It looks like too much. We cannot use this as a timestamp and guarantee you the sequence of the number. For sure we can bring some network protocols, I mean like time sync network protocols like NTP. And if you look in details how it works, so first of all, one of the main limitations is the number. So accuracy of NTP is only 1 millisecond. And for example, if you have a transactions in one server, and you want to make sure like it's the same this time across all of the nodes, you have to wait at least additional 1 milliseconds to make sure that it will not appear as a duplicate of sequence number. So it means like for NTP, you can guarantee only 50 transactions per second. Not sounds like good from scaling perspective. Let's look in details. What's the problem? Why we cannot make more accuracy from from the time sync perspective? So, you know, like first time when I look at this, all of this stuff, I mean like the timing, it sounds like, yeah, it's so easy. I have 2 instances and make the synchronizations of clock, it's so easy. But in reality, first of all, we don't know what is the propagation time. What is propagation time? So you have 2 servers, for example, and you want to sync between them a time. And you send this traffic across the whole network, across your switches, for example, other hosts, network devices, so on, so on. And you need to somehow predict what will be your propagation times. Current realizations in PTTP and NTP is like send across the whole network this signal and calculate average of propagation times. And at this propagation time, that's when you send your time sync signal and when you receive it. Like it's a difference between them. But in reality, if you look at what the problem can be, so first of all, if you have like a couple of the servers, it sounds like super easy. Again, like you don't have high load, you don't have a lot of customers, don't have a lot of resources, like I mean like network switches and so on. Another problem can be that some hardware does not support timestamp when they got this message, when they receive this message, when they send these messages. So it depends on hardware realizations. It can be very difficult to calculate these propagation times. So it's very difficult to set like, okay, I send this time sync signal in this specific of time. And another one, it's reliability. Reliability, I mean like, you can imagine how many resources we have in AWS. So, you know, interesting fact from AWS, we calculate these propagation times, and just temperature can affect these propagation times on your devices. Not only some switches and hardware and busy of the host, but also the temperature of this host, the temperature of your network switches. So we decided to inspire ourselves to look at other solutions. And it's not a joke, so it's seriously, we decided to look how Adroid Collider works and how they working with timesync, because in this place, it's mandatory, it's must have to, as much as possible, accurate of time. So, and the solution is just like to work on hardware level. You remember that I said like for virtualizations, we use a Nitro. Nitro is our custom chip. It also is software realization, how we work with the Nitro. So we decided to upgrade a little bit of our Nitro chip and include the specific chip which will be responsible only for one single task, it's time sync. And for sure, we thought like, okay, if we send this time sync signal across current network, we cannot guarantee that we will sync between two hosts with accuracy, like for example, 1 microseconds. So for that reason, we decided to create separate network just to sync time across EC2 instances. And this is an example of the time sync rack, which is not only one, it's multiple of the racks in one availability zone and across multiple regions. So on the top, you can see a reference clock. Reference clock, it's connected to a satellite of atomic clock, and the accuracy of this reference clock is around a couple of the nanoseconds. And for sure, we have a redundant model. This redundant model helps us to save this accuracy of the time when we lost connect to atomic time. So, but at the bottom, you see also our custom distributed network network for time sync. So let's look in detail what's inside of this box. So again, this is one, it's our Nitro, it's Nitro chip, where we do this additional model just like to sync our data, and you see FPGA chip. So you don't see anything related to the network, a standard network configurations, because this network does not responsible to send your network packets like classical TCP, IP, and so on. It does not have any drivers, does not have any operating system. It just do only one job, just sync your time. And the accuracy of this mechanism is 1 microsecond. And if you remember limitations from NTP, 500 transactions per second. And as said, it's too slow. But with new approach of time sync, it's a little bit more. You can calculate 500 increased to 1,000, so 500,000 of transactions. Sounds more scalable. So again, the main idea of that separate network, separate devices, we're responsible just to sync your time across EC2 instances. For sure, it's not only our technology you can use if you our clients. And also I want to highlight it, it's currently I see a trend across open source. For example, the guys from Meta working very close with PTP, a new network time sync protocol, and created their own custom hardware. If you want to implement something like that, you can like open their solutions, use their hardware, but our secret weapon to be consistent is time sync.
All right, let's summarize it. And let's get back to the question that we asked in the beginning. How do we scale our database to millions of writes? Well, if you find yourself in the situation like Victor mentioned, that you have to do this ASAP, probably you better go with one of out-of-the-box solutions. But if you are planning in advance, here are some things that we mentioned that we did in AWS. So first of all, we started with cloud-native architecture by separating compute from storage. This in turn allowed us to do some database optimizations. One of them that I mentioned today is that we only write the redo log records, and then the storage itself creates data pages for us, which we read on the database engine level. So that's not the only optimization that we have done, but all of them actually come from this specific architecture. And then finally, when we started doing sharding, we faced three main challenges. So the first was, how do we manage our custom routing? And here we have created lightweight routers that only contain small portion of metadata and can scale vertically and horizontally. And we decided to make each of these routers a database so that it can orchestrate complex transactions across multiple shards. Then the second challenge that we faced was, how do we do the resharding and how do we scale our shards? And in this case, we have went with a hypervisor that supports oversubscription for the scale purpose. And then we went with the functionality that again was based on the recovery functionality of the storage to instantly create a new shard. And finally, to handle the distributed transactions, we decided to go with the wall clock approach. For that, we had to reduce the error bound to increase the number of transactions per second that we can support. And in turn, to achieve this, we had to create our own time synchronization infrastructure. I hope this provided you some ideas and some inspiration of what you can do if you face similar tasks. Or if not, if this is not the challenge that you have in your day job, at least provided some interesting insights into how we in AWS handle the high-load challenges. Thank you very much for your attention. Please don't forget to fill in the survey, and we'll be happy to take your questions.
Thank you, guys. I know that, yes, first question, of course, from Yandex database.
Ooh. NDA. Sorry.
Either here. Great talk.
Please go ahead. Sorry. It's like because we listened to your topic, your sessions. It's like I expected your question will be like 500 level under the hood. Not sure that we'll be able to answer, but let's go. Let's try.
First of all, thank you very much for a very interesting talk. Both the talk is great, the topic is very interesting. And I would like to ask you a question about guarantees. I would like to ask if your database is serializable. I mean, your transactions, are they strict serializable? I mean, both serializable and linearizable. That's the first question. And the second one is about performance, of course. Do you have any public data with, for example, TPCC results? Actually, there is a third question. Do you have Postgres compatible API? So if I use Aurora, I don't have vendor lock except performance lock and limitless pricing. Oh, sorry, limitless performance.
Again, like one more time back. Postgres and MySQL.
I batched. Sorry, I batched.
Postgres and MySQL fully compatible for Aurora, so you're not locked in with AWS. You locked with AWS only from scaling perspective, like what we show. For example, if you need to store, 100 plus gigabytes, terabytes of data, you can do it. Replicas 15, and also the scaling. If I right remember, we don't need to double check with our blog post and documentation. Do we have some official benchmark, like based on your evaluations, what you show in your previous topic? I don't know. Need to double check.
So I can add here because I was doing a bit of database testing. That's why, by the way, your talk was very interesting to me. So we in AWS, we of course do some testing internally, but usually we don't publish the benchmark results because overall we don't believe in benchmarks. We believe that it makes more sense to look at specific workload. For example, I was testing MongoDB with one of our processors, Graviton. And I compared it to Intel and AMD. And the results were completely different, even though I used YCSB in all the cases. I was always configuring it with different data access patterns, and the results were different. So that's why here we don't publish the benchmarks themselves. So we have some figures that are published on the website, it's about 20 to 30% performance improvement compared to the vanilla engine. But I would say it's always case by case. So when I work with customers, sometimes it's better performance. Sometimes customers already have customized, for example, their Postgres settings so much that it's almost the same performance.
Okay, I see. So, and now the last question is about guarantees, about serializability, linearizability.
So basically, Right now, unfortunately, I cannot answer this question. So because this service, it's still in the preview. So what we have shown you, it's not yet even available to the customers. So yeah, sorry, I cannot answer that yet. But hopefully, like in the matter of this year, we will have more information available on this.
Some questions you don't really answer with the microphone on your head. Yeah, no, please. Yeah.
Hello, thank you for the presentation. It was quite in depth, it's beautiful. And you said that we have a buffer cache in a separate process to the database.
Yes.
And we access via network.
Sorry?
And as opposed to Postgres that accesses it directly from its own memory. Why is it efficient and how much performance penalty do we have?
Sorry, probably I just formulated not like fully clear. So what I was meaning is that it is a separate process, but it runs on the same node. So basically, it's like a neighbor process, but the reason why we have done this is, first of all, because it allowed us to take this buffer cache and actually replicate to other nodes. So we don't do this just for crash recovery purposes, we also do it, for example, for the read nodes, because in Aurora we can have just one, if you don't speak about Aurora Limitless, I mean like regular Aurora, so we can have one writer and up to 15 read replicas. So first of all, we use the buffer cache for this purpose. And therefore, it has also helped us to actually build this crash recovery functionality. Sorry, I forgot what was the second part that I wanted to say.
That's it. Thank you.
That was it. Okay, thank you.
We have some time for one more question. And then we'll take the mics off and then you can have the full discussion.
Hello, thank you. I have several questions. One will be interesting enough regarding Vitess open source software, and it looks like you are creating something similar with VTGate, which is proxy actually, and the routing tables to distribute shards. It's okay. So, do you have plans to somehow collaborate with PlanetScale, which is I know available on market, or you see as competitors for you with Vitess software? What's your opinion about Vitess approach regarding the same problem to distribute queries between different charts and actually provide a compatible interface, but only for MySQL, of course? What's your strong points against Vitess software? Thank you.
Mm-hmm. So basically in AWS, of course, we have nothing against open source software. We love open source. That's to answer your question. And of course, like each time when we develop something new, we take a look like if we can use some existing solution. So in this case, basically the thing was related to scaling. So I think it's not just like it cannot work on the scale that we expect. Regarding the plans, unfortunately, that's not something we can answer.
Okay.
So we are not disclosing the roadmap. I'm sorry.
Okay, thank you. And my second question will be more financial one, because this is where the trickiest part I think happens, because this is good software, but how much ECUs used on biggest productions that you have that rely on serverless software? I'm not trying to to highlight the price of serverless versus provisioned version of Aurora, but it's very interesting to understand what's your approach. Is it working solution for for big companies who rely strongly on Aurora database? What's your approach? Is it okay to go into serverless version? How much ECUs would recommend to keep? And what's the perfect match between price and the complexity of software? Thank you.
Thank you for the question. So my personal opinion, so I'm as an architect used to work quite a lot with customers, now unfortunately not that much, but what I have seen regarding your question, like comparing serverless and the provisioned one, is that it doesn't really depend much on the company as it depends on the use case. Like for example, one company that I worked with, their load is pretty stable because they have users all around the world and they have different notifications, recommendations and so on. So for them serverless makes almost zero sense because yes, there is some overhead, but it's so small that they don't have these spikes, for example, like in the morning or in the afternoon or whatever. While, for example, I have another customer who is a public sector organization in the US, and they work with students and they organize some competitions for students. And of course, their load goes hugely when the competition starts. So for them, Aurora makes sense, even there are like loads of students, well, of course, public sector organizations don't really pay money themselves, but still, that's a huge load, and the price is actually very reasonable. It's much cheaper as compared to the physical database, provision database, if they were doing so. There is like no one answer here, I would say serverless better fits when you have spiky workloads, the same as all the serverless stuff. Like, for example, you wouldn't go to Lambda if you have like the constant load on your system. Most likely you will go with something like containers. So it's quite the same here. Thank you.
Thank you, guys. So
I think
it was
organizers
amazing.
asked that everyone stays here after our talk.
We just need a minute of your time. We'll play with the screen and show you a little cartoon, like all the parents do. But we'll use this time also to take the mics off, so that you can, after the video, you could go to the discussion zone. Let's give another round of applause to our friends from Amazon. Thank you, guys.